Okay, math analysis. This is the final review, the calculator OK part. This is problems 1 through 5. Problem number 1 is actually a multiple choice. Solve and express in interval notation. And I give you a hint to just get all the terms on one side and graph it. So what I mean by that is just move the 1/4 over, so it'd really be 4 minus a fourth. There we go, once my computer starts working. So this would be, let's just leave it as 16/4 minus 1/4, so that'd be 15/4, plus 3 over x minus 1 is greater than 0. So I'm going to graph this now, and now remember, I'm just going to graph this side, and I want to know when all this stuff is bigger than 0. So I'm going to see when the graph is above the x-axis, because whenever I graph this, again, I'm going to graph with my calculator, but if I start graphing this, whatever it ends up looking like, wherever it's above the x-axis, that means the output of the function is greater than 0. Anything that's above the x-axis, positive y values. Negative y values mean it's not correct. Positive y values, negative y values, positive. So we're only concerned about when it's above the x-axis. So again, you have a trusty calculator for this. So in my y plot, 15 over 4 plus 3 over, and put this in parentheses or whatever you got to do to make sure that this is in the denominator, x minus 1. And I'll go ahead and do zoom standard just to give myself a starting point. Okay, now again, remember, I'm wanting to know when I'm above the x-axis. So it looks like it's above the x-axis forever until it gets right to that point. And if you kept expanding your x's in the negative direction, it would be. So it's above, above, above till right there. It'd be real nice to figure out what right there is. Well, then I can use the zero finder. So second calc, use the zero finder, and looks like my cursor right now is above and to the right, and so now it's, sorry, it was to the left and now it's to the right, and I get a 0 of 0.2. So if you look on your possible answers on this one, it's 1/5. So let me do a quick little sketch of kind of what that graph looked like again. My perfect straight lines. So it looked like the graph was positive forever and then shot down. This was one-fifth. So part of the solution is, and again, you can, if you're looking at the multiple choice answer, you can probably figure out what it is at this point. Negative infinity all the way to 1/5. So from negative infinity to 1/5, any value there seemed to make it positive, made it greater than 0. And then if you look, it picks back up. Let me get this to work. There we go. It picks back up, and actually there's an asymptote here at the number 1. At x equals 1, there's actually a vertical asymptote. If you have an older calculator, it might have graphed it. And that makes sense because if x was 1, we'd have division by 0. Uh-oh, can't have that. So there is an asymptote, but then it picks back up, and we're above the x-axis, and if you kept extending this, this is above the x-axis forever. So again, this is the asymptote at 1, So it was from 1 to infinity that it stayed above the x-axis. So again, that other part looked oh, no, that's not the color I wanted, but that's okay. And again, there was an asymptote at x equals 1. See if at least this color works. There we go. There was that asymptote at x equals 1, but then again, we're above the x-axis forever. So that is 1 to infinity. So there's my entire solution set, and that's has the union in between it. So the answer was D on that first one. And again, solving this algebraically is pretty nasty. Use that calculating device. It's definitely helpful. Number 2A, this is a little bit easier problem. Find the inverse of this. All the inverse is where the x and the y flip. So I'm just going to rewrite this as x equals 2 y minus 4 squared. Again, that's all the inverse is. Just flip the x and the y. Now I just need to solve for y, though, so it's in the normal functional form that we're used to. So the first thing I would do is divide by 2. We'll get some colors involved here. So divide by 2. So that's gone. Now I would square root both sides. There's a square root, nasty square root. Now, do realize when you square root, you get plus or minus. Don't forget about that. So let me write what I have now. So right now I'm at plus or minus root x over 2 equals, I square rooted this, y minus 4. And then simply add the 4. The 4 will not be in the square root, though. Add the 4 over, and you'll end up with y is equal to plus or minus square root of x over 2, and then outside the root plus 4. There's your answer. And technically that's two answers, positive and the negative of that. Now if you want to check this, again, fancy calculating device, I'm going to first graph the original function, which was a parabola, 2 parentheses x minus 4 squared. And I know I'm going to get a parabola there. Then I'm going to graph the next two things that I found. Namely, I'm going to graph positive root x over 2 plus 4 and negative root x over 2 plus 4. Just that accounts for the entire inverse, the entire blue part. So square root of, and again, make sure this is all in the square root if yours doesn't open up a parenthesis like mine did. X over 2 plus 4 and negative root x over 2 plus 4. So again, y2 and y3 here are both really just the inverse. So I'm really looking at y1 is one thing, y2 and 3 accounting for the other thing. And if you graph this, you get an up and down parabola. This was our original machine right here. This is our inverse. And if you remember, a graph and its inverse should reflect over the line y equals x. So if I add in the line y equals x, you can see how it slices through there perfect. And if you tilt your head to the right at about a 45-degree angle, these are perfect reflections of each other. Now granted, remember your window's kind of skewed here because it's more elongated than it is up and down. A way you can double check is actually there is zoom square. which doesn't stretch any of the axes. It keeps it perfectly in proportion. Now you can definitely see that the two graphs, the two parabolas, are perfect reflections of each other. That reflects to that. That reflects down to that. It all reflects perfectly. So that's a way to check. Again, you don't have to if you feel real good that you did it right, but it is a way to check it. Okay, 2b, if it'll let me go on. There we go. 2b is a little trickier, but same logic. I'm going to flip the x and y. Remember, this really means... Oops, come on, let me have my pen. F of x is really my y value. So flip the x and the y to start off with. Now, oh my gosh, it's 2 spots. That's what's going to make it a little trickier, but we'll get there. So x equals y over y plus 1. Okay, so, and again, this one's a little trickier. First thing, fractions kind of scare me, so I'm going to multiply by y plus 1 over here. That's gone. And the only thing I can think to do is distribute, because again, I'm trying to get y isolated. It's in 2 different spots now, and you'll see what we'll do in just a second here. So, if I distribute the x through, I'm going to have xy plus x equals y. My y's are on different sides. It'd probably be smart to get them on the same side. Get some color in here again. So I'll minus this xy over here. So I'm left with x equals y minus xy. Okay. Y is in 2 spots here, but it's a common factor, 6-letter F word. I can factor it out. So this is y. If I factor a y from this, I have 1 left. If I factor a y from this, I have x. Now, y is by itself. Remember, I want to get, well, I'm sorry, it's hooked to this, but there's only 1 y left. I want to get this isolated, so I would divide by 1 minus x. Oh, there it goes. Not supposed to be 2 bars there. 1 minus x, 1 minus x. So you end up with x over 1 minus x equals y. That is the inverse of the original. They look somewhat similar, but definitely not the same. That's your inverse. And you could double check this with graphing. It gets a little nasty, but you could graph that and then separately graph that. Again, just like on the previous problem, it should be reflections of each other. They should look the same folded over the line, the diagonal y equals x line. Okay, number 3, you will not have an easier problem than this. And there will be one like this, so this one should nail. If negative 3, 7 is on the graph of y equals f of x, name a point on f inverse of x. All the inverse of a function does is flip the x and y, so this is how easy it is. Flip the x and y. 7, negative 3. That's got to be on the inverse. So all you do is flip the x and the y's. Done. Next problem. Number 4 here. Find h of, get out of there. Yeah. Find h of negative 3 when h is, this is a composition. Remember, you read these backwards. So I work the G machine, get a result, then I work that in the F machine. So h of negative 3 means plug negative 3, since it says this is what the H machine is, plug it into the G machine, and then take that result and plug that into the F machine. So if I plug negative 3 into the, remember, because you read it right to left. if I plug -3 into the G machine, the result, so this is like doing G of -3, I end up with just, hey, conveniently, that's -6 plus 7, that's 1. That is the result of the G machine. Now I take that result and I plug it in for the variable in the F machine. And so obviously this is an easier number, but let's just act like we're not sure what it is. I plug it in. And so obviously 1 cubed is 1, so 3 plus 2 minus 1, 4 is your overall result. So again, remember with composition, that little O looking thing, you read it right to left. Plug it into here, get a result, then take that result and plug it into there. If it makes it a little better, this could also be written as F of G of -3. That's what H of -3 is, by what it told us. So again, not a terribly difficult one. Obviously, if the number was different than 1, make it a little more complicated, but still just plugging it in. Okay, 5A and B are asking if the function's even or odd. Even, and it gives you this on the directions, just as a reminder, even means that if you replace x with -x, you're going to get the exact same result back. It makes sense to call it even because if the x's are to even powers, it's probably going to work. So just to verify this, I'm trying to see if I get the exact same machine. So if I plug in y, I'm sorry, I didn't plug in yet. If I plug in -x instead of x, oops, more erase that, hold on. Negative, oh, and I don't know what happened, there we go. -x squared minus 7. Negative to the 4th power is going to make it back to positive. Negative to the 2nd power is going to make it back to positive. Lo and behold, I ended up with the exact same machine. So that means that this is even. It's an even function. And again, fancy graphing calculator thing. Let me get rid of all these other plots. Okay. An even function graphically means that it reflects over the y-axis. So if I graph it, just as a check, 3x to the 4th, let's see, plus 2x squared, minus 7, and I'll just do zoom standard. This is reflected over the y-axis. It's symmetric. Excuse me. It's symmetric over the y-axis. Since it looks the same on the left and the right of the y-axis, that is also a verification that it is an even function. (5b), go figure, it's going to turn out that it's an odd function. But first, let's say I just thought maybe it was going to be an even function. Again, if it's an even function, that means you replace the x's with -x's and see if you get the exact same machine. So again, this is not going to work, but I just want to show you what's going to happen. So I don't touch the y's. Again, I'm testing to see if this is even. Wherever I see an x, I replace it with a -x. -x, it's a negative. Y equals -x squared. Again, I just replaced the x with -x. So if I start to crunch this down, there's a negative multiplied by this, so that's -3xy equals, okay, that negative stays. Negative squared is positive. See, I did not get the exact same machine back. There's the positive, there's the negative. So this is not even. So the other thing I can test for is it odd? Odd, you'd think, oh, so I replace the y's with negative y's. No, it's actually replaced the y's with negatives and the x's with negatives. So if I replace every y with a negative y and every x with a negative x, I'll see if I get the same machine back. And again, I'm doing this baby step by baby step. A lot of times you can, just intuitively look at it and sort it out in your head. So everywhere I saw a y or an x, I replaced it with a negative of that. Well, squaring the negative y means positive y squared. And then here's what happens. Oh, negative times a negative is a positive. So that's plus 3xy. Negative there stays. Negative x squared is, again, just x squared plus 5. And lo and behold, same thing. So since that happened, that tells me that this is an odd machine. I don't believe this is a function because that y squared, I'm not absolutely sure, but it still is an odd machine. So there's 1 through 5 on the review. And when I come back, we'll do some more.